that works? Okay.
Now you know.
Now I know. The project started in October 2021. It has 42 months of lifespan, and it will end next March of 2025. So basically, we are in the last, let's say, reporting period of the project. So we are already having pretty good results that we want to share with the community and with our stakeholders. It's a project in the framework of Horizon 2020 goals and the Green Deal framework. And we have partners from 7 different countries, 19 partners in the project. Our ambition here is to boost technologies from Material 4 to Material 6 in the project. And the project is coordinated by RBCN, myself presenting, David Perez, and my colleague Steph here. What is Hypergryd? What is our objective? First of all, our core objective is to develop and to integrate renewable energy-based solutions to empower a smart hybrid energy networks. Our goal is to optimize all the value chain in this ecosystem, so from system design to operation, to ensure the flexibility and rapid deployment and guarantee a robust and secure energy supply, and to enhance the user participation in all this process of overall grid energy management. And as a latest, but not less important, to develop a single platform that can operate as a hub, so concentrating all the efforts that we have done from the software point of view of the project in a platform that can operate and integrate all of this. The project itself, from the hardware point of view, had the idea to integrate a wide range of technologies, namely hydro plants, wind power plants, biomass boilers, solar PVs, electric batteries, thermal energy storage, CHPs, and so on. And as a project, in terms of technology development, we focus on 3 core technologies. That is the modular heat pump with short-term PCM storage as a, let's say, as an inertia and operating heat pump of the project, renewable energy source-based source and storage, and CHP, a small-scale CHP with a steam engine and a steam buffer to operate in the system. As a, let's say, parallel and part of the project, and exploiting the synergies from technology development from the hardware point of view and from the software point of view, I will be brief here because it's the core topic of our workshop today. But we developed a platform that integrates, let's say, an ecosystem of tools that basically operates in the whole value chain of district heating and hybrid coupled district connections. In terms of living labs, that is how we call the demonstration activities that we do in our project. We have 4 living labs in the project. MB Park, our host today, is one of it. The district heating and office network here. We have a residential district heating in Sonarplatz. We have the Kesor Research Center in Poland, and we have the URAX facilities also here in Italy. And from a general point of view, this is let's say the general scope of the project Hypergryd. Now I will give the floor to our colleagues from IDP and from encoord to present part of the solutions that we are developing as part of it.
This one. Sí.
Okay. Hi everyone. Well, I'm Jorge Liao, I'm from ADP. We're speaking about, we're talking about the Hypergryd digital twin platform. It's a platform of platforms that connects all the platforms that we have, the tools and services that we have applied to the MB Park and Soren Platz demo sites in only one. The first thing, what is a digital? The platform is ICT architecture is focusing the digital twin SaaS platform, or what we call platform. What is this? A digital twin. The digital twin is a virtual copy of what we have in the physical world. For example, here we can represent all the buildings from MB Park, the thermal network, as well as the electric network and the energy producers. The platform service capabilities allow us to have a complete developing environment that has all the information that, for example, encoord and get two or two need in only one database. So we can share the information without having to go to external databases. The software as a service allows to have the other two softwares inside the same platform. So you don't have to jump to another platform to look for information. You have to go to the other one. So you single sign in into one platform and you have all the information you want. The main capabilities of that we develop in the Hypergryd, you want to have the BD2. It allows to be okay.
So they can
Okay.
So
It allows to create new living labs. So we can create the digital twin representation of them. Like this is how you create it. You have like, you put only the longitude and latitude and it locates the living lab. So you can start drawing the different buildings that you have in you want to represent the grid. And you do it like this, you can, it doesn't look like, you have like, you can name the different buildings, you can put the cadastral code, because that's really important when you want to, after you create the simulation, you have the digital representation, you want to build the actual network, you need all this information for the government to build it. This also allows to create the different networks. The thermal and electrical is as simple as connecting the different buildings that you create. So you can put the distances, the nodes, and then you can update the information directly in the node. You can click the different nodes or branches in the network and update the information. And that information can be extracted by the different tools that we have in the platform. You can also download this information if you want to go to external software like QGIS or ArcGIS or Esri. You can do it. You can download it and you see all the information is right there. So this allows more integration with different platforms. Not only it doesn't limit this information to this project, but also if your company has another software that can use that information, you can use it. So you have to model again, do all the process. Then to integrate with encoord, we create this tool that after you create the network, with only one click, you can convert the network that you design to the encoord model. So all the information, it converts information to the GeoJSON format that we agree on. And he extracts this information to get the simulation that I'm going to present at the end. What tools to be integrated into the platform? We have modeling simulation software designed to simulate the operation of integrated energy system that couple energy and electrical networks. Additionally, we have the exergy-based analysis and assessment energy conversion system. For the district heating and cooling, we have the open source software solution that enables cost-effective heating and coordinating energy management among community members. And we have a local peer-to-peer energy trading simulation. We were allowed, we could integrate all these softwares in only one solution. Otherwise, we will have like, you have to, as a user, you have to go to the get to in one platform, then you will have to go to the grid singularity, then you will have to go to the in here. Here is the different integration methodology we use in the project to integrate all of them. We have the backend, there is a server-side integration, then we have API that it basically works as a receiver, with several steps for doing a process. And we have a simple link integration also. If you want to integrate another software, you can actually only, if you want, you can only use your URL and integrate the platform. In the project, we use this ICT integration flowchart, how the process works between the different tools. And you can see the encoord tool is directly in the Hypergryd core server. And then we have the get tool, it goes to exporting the GeoJSON file and HTTP communication to the web API. And the GTH also is working through the web API as well. And then we have the grid singularity as a simple link. But this allows us to have the Hypergryd architecture, that we have the core service of the platform, that is a tree viewer where you can see the detailed thing of the living lab. Then we have the Hypergryd services. These are the ones that are fully integrated into the platform. Then you have the external services. Those are the ones that can touch the information, but not fully integrated into the platform. Then we have the external data. That's the data that you can visualize in the platform, but you cannot modify it. And then you have the Hypergryd data. This is the one that is more variable and can be updated. Here are the results that we have in the Hypergryd project. You can see, you can visualize all the buildings in the Sun and Platts demo site, as well with the cadastral information. You can also visualize the results from the tool without having to go to the platform. You can visualize all this in here. It gives you the information from the node, the branches, and externals. Then you have the monitoring system that from the smart meter, from the KDH2. You can access the grid singularity platform also as well from it. And then we have the MV part. You can visualize the different buildings, the energy closers, the thermal network, and the electric network. Then we have the encoord one for MV Park, also the same as Sony, as well as the electric simulation. And that's it. If you have any questions regarding the presentation.
There are some questions from online. Okay, the first one, but maybe Nicola might be answering this later on, is how does it work, the thermal network simulation?
We will have an example later on.
Yeah.
The steady state, the quasi-dynamic analysis for the end part is.
Okay, so hopefully the people online will work it out. So later on in the next presentation, there will be some information about it. And the second question is, could you use a CURIT portal for the customer's point?
Okay. For that question, I will have to get back to you. Since yeah.
Okay.
At this moment, I don't know. I have to look it up and get back to you.
Okay, thank you. And last question, they would like to see any of the digital twins if possible.
Yeah. Yeah, this one is day one for MB Park.
Yeah, we can try from the back.
Yeah. Okay, go to the. Yeah, this one is.
And while this is running, there is another question. Is the platform already accessible? Is it free? And this is a question for the coordinator. You have a plans?
Well, actually, this is from the probation point of view.
Well, actually, I was about to ask this question in a more wider terms. So yesterday, because this is the result or one of the results of a research project, so our results are not yet on the market. Some of our results are relatively low technology readiness level. Some are higher. The platform, what you have seen so far, is among those with a high technology readiness. So I understood yesterday from the discussions that it is ready. Okay, so it is something which is ready, and the business model, how users will pay, is still under definition. I'm looking at your colleague to understand where you are with this, and my conclusion yesterday, or my understanding, was that this will be defined before the end of the project. So somewhere, let's say, along the next 6-10 months is more or less. Do you confirm? Okay. So this is where we are. When it comes to the tools connected to the platform, so we will be seeing now the encoord simulation tool. It will be also, it will be not for free. There will be a business model behind. So from the platform, you will be able to access this simulation tool. And here as well, we are under discussion about how the pricing will be. So it is a bit too early now to tell you exactly how much it will be, but it is something which will be soon available at least. And I think, Ilaria, we do have all the emails from the participants, so it will make sense that we keep them informed somewhere over the next 10 months as things are really operative.
I don't know whether there are any questions from the floor. I think that we can proceed with the next presentation. Thank you very much.
There we go.
So, good morning, buongiorno. My name is Nicola, and I work for encoord, which is in short for energy coordination. And we have been quite thrilled in being a partner of the Hypergryd consortium, and I will show you why in a few slides. We are going to talk about SAINT, and I will try to explain you why it's much better to call it SAINT instead of its real full name. The acronym, it came out by chance, but it turns out to be very effective. So let's go. Yep. We try to have this session as much as interactive as possible. So we complemented the presentation with few questions, actually there are 3, that you may answer using that QR code or this Lido platform. So if we are talking, you're gonna take few minutes to try to go online and answer the questions. The first one is quite straightforward. Do you or does your organization use any dedicated software for planning and designing energy systems or energy networks? Clearly, these questions is assuming that you are working as the kind of stakeholders in this particular context of energy infrastructure. It doesn't matter. Yeah, sorry. Yeah, it doesn't matter. It's just very much general. It's just to understand and to point to the fact that it's not the old times. We need software tools in order to be as efficient as possible and as accurate as possible. I really enjoyed a lot the tour of 2 days ago that Mauro organized for us, because he started from the Frejus monument. So it's not that time when we were just building using pencil and paper. Now it's ICT period. Clearly, within the activities of Hypergryd, encoord supported the project by extending its main product, SAINT, with new capabilities, both in the direction of electric simulation and thermal simulation and integration of electric and thermal, with existing capabilities of analyzing gas infrastructure. I always like to start any talk about the company, the projects, the products by showing the faces of the people, only because we tend to forget that companies are not just entities, but are people working together. And the team here, it's pretty different, pretty complicated also in terms of ages. You can spot some white hair there and also some young faces. Our most internal big challenge is the language. We are 22 and we are speaking around 20 different languages. English is, for now, the reference one. But this just to tell you that this variety of people with different background have huge potential to address a variety of problems in a different way. And this is a great capital on which you can build. In terms of customer, well, we cover electric and gas utilities, asset and technology developers, and engineering, consulting, and research firms. That provides a little bit the type of variety of problems that we are able to address with the tool and with the consultant services that we provide and with the data that we provide. Some examples. Well, let me do this so that everything goes out at the same time. Well, you can see here examples of application of the software. And that goes again in the direction of stressing that it doesn't matter a lot what type of energy carrier you're dealing with now or which type of energy infrastructure you're looking at. We are able to cover a lot of them, and this know-how has been transferred into Hypergryd in the context of electricity and of thermal analysis. Examples, NREL is a US research institution at the federal level We worked a lot with renewable integration. ensource is a private company dealing with hydrogen. National Grid is one of the biggest transmission system operator, integrated utility, gas and electricity in the east coast of the United States. They have also a branch in Europe, which is a transmission system operator of Great Britain, National Grid. Sumitomo International Company, dealing mainly with energy storage. ConocoPhillips, electrification strategies. Enverus is a financial consulting company, which is using the product for electricity price forecasting. So variety of applications. And before arriving to some examples directly using the software, let me provide you some general elements. First of all, you will understand why I really like much more the use of the word saint to indicate the product than scenario analysis interface for energy systems. It's too long. Saint, it goes directly to the point. Here you will see that the core functionality of saints are around two general classes of problems. On one side, it's optimization. On the other side is physical simulation. In the optimization context, Saints allows you to address production cost modeling. So addressing problems related to market and the operation of the market. On the other end, you also are able to do system expansion. So planning for how you can develop your infrastructure in the next 5, 10, 15, 20 years, whatever you want in terms of time horizon. And in both cases, Saints joined forces with another software company, which is the one selling the product Gurobi, which is one of the industrial numerical solver and optimizer out there. In terms of physical modeling, we move from here, electricity in terms of both distribution and transmission with AC and DC analysis for power flow. For distribution, there's also the module, which is addressing not only balanced ACPF, but also unbalanced ACPF. And then we have the other two. The initial core capability of Saint when it was started as a project in 2018 is around gas. And then, especially with the help of Hypergryd, we complemented everything with thermal simulations. We developed the software in a way that follows modern philosophy in software development. So essentially, you have on one side the core functionalities that are embedded in the solver, and you can interact with the solver through an API. And this is what it's been implemented in the platform that Jorge showed you before. But clearly, you can put on top of the solver also a graphical user interface that is what we will see in a few minutes through some examples. And you can use that either from your laptop or from your workstation in the office. This slide helps me in demonstrating our main contribution to the project. So why encoord was involved in Hypergryd? Well, we were in charge of one task, 3.5, which is the development of an energy network modeling tool to plan and operate coupled gas, electricity, and thermal networks. And this is where Saint was fitting well. And this is where we learn a lot from the Hypergryd project in terms of understanding what kind of problems a thermal modeling should address. So what the project was doing for us and is still doing is providing real problems to address, indicating what type of workflows to use to address such problems, and allowing to validate models and workflows so that when you go on the market or you want to present your solution, it's not just a generic tool, but it's something that is supported by experience of people dealing with those kinds of problems. Here there is another question for you, and I hope that at the end of the presentation we can go through the results a little bit and see what kind of input you may have provided. What do you value the most in a technical software? What I mean with this is when you use any technical software, it could be MATLAB, it could be, I don't know, Synergy Gas, Pipeline Studio, whatever. Are there any elements that you really like to enjoy? Like, for instance, accuracy in the models, mathematical, rigorous description of the equation, a nice graphical user interface, the capability of bringing in or out data easily, the possibility of integrating different data sources in just one place. So this is, I hope, the kind of things you may point. There are some examples in the questions online. And the reason is that we, as a software development house, believe that a lot of these elements are really important because you should not spend time in bringing data in solving ICT problems related stuff. You should use your time to solve your problem and your challenge because that's what you're paid for. We will go through some examples. First, we will start with this mock case of a gas and electricity transmission system that will allow me to showcase some of the main functionality of the graphical user interface. Then I will show you a simple example of this municipality in southern Germany, Schüttenwald, where we can see the gas and electricity and thermal distribution system. Then we will have a little bit of more fun with MV Park, the electricity and thermal distribution system. I just want to point your attention to the note at the end. So whatever numerical result you will see, those are not, let's say, real data. They are just numbers that I put in the model to have something that can run and to show the capabilities. And that's another question that we will see later on. I need to go back to this, and now I have to share this screen. Okay. Yeah, need to figure out the way of putting this away. Okay. I already launched Same for You. Unfortunately, even if this is a 64-bit application developed on a Windows platform, we are not Microsoft, so we are not able to force you to load in the background in the RAM many things that gives you the impression that when you launch Word or Excel, everything is so snappy. Just because half of the stuff is already been there, and that's why you need 32 gigabyte now, maybe of RAM for running your laptop. The graphical user interface helps in understanding the general logic that Saint uses for building and running simulations. It is divided in the upper menu part in network, scenario, and simulation. So basically what you do is first you develop your infrastructure, your network, both from a geometric point of view and from a topological point of view, adding elements depending on the type of network. For instance, in the gas system, you start drawing pipelines, and then at the nodes, you may add also, Jorge used this expression, externals, so that you add demand points, supply points, other type of facilities like gas storages, for example, gas fields, LNG terminals. In terms of linear facilities, you do not have only pipelines. You can add compressor stations, gas valves, control valves, resistors. All this gives you and covers nearly 95% of the objects that normally you can find in other software dealing with hydraulic modeling. Our main competitor in Europe is a software called Simone, used by more than half of the transmission system operators and distribution system operators in modeling. And on the US side is called Synergy Gas. While I'm talking, I also do another thing, which is loading the project. It's going to take some time. Once you have your infrastructure and you have all populated the infrastructure with all the relevant data about the facility, then you move conceptually to another stage, that is the development of a scenario. A scenario is a set of conditions that you impose on your objects in order to solve a specific problem. For example, in a gas system, scenario could be, I want to this supply to receive a certain amount, another amount from the LNG, and I need to distribute these other amounts to all the demands points. I need to operate the compressor station up to this level. Now, let's see if these conditions can be met by my system, or if I need to improve my system by adding new facilities, or if I have the possibility of saying my system can give even more. So as a transmission system operator, I can sell more capacity and my business can increase. In this example, I'm showing you basically two fake networks. One is a gas system. Here, I'll just do this so we can see it better. On the left part of the window, you see this, it's called Model Explorer. It is a tree-like structure where you can navigate your network. In this case, we have a gas network that is called GNet 2121, which is made out of 21 nodes. And here you have the list. At each node, you may have maybe nothing, like this node here, or you may have externals, like in this case, there is an utility or an exit point. It could be city gate, it could be whatever. And we have 26 branches, 25 pipelines, and one compressor station, which is this symbol here. Whenever I'm selecting, let's see this. Whenever I'm selecting an object in the property editor, I can access all the relevant details about that specific piece of infrastructure. For example, for this compressor station, you may see you have an inner diameter of the underlying mathematical model or description that has certain properties. And here you have all the other details that are covered by the model related to maximum driver power, shaft power, or mechanical efficiency, and so on. So a lot of details. The same things if I select in the pipeline. This will change. Here you have details about thickness, diameter, length, roughness, and so on. Let's not get into details about this. What is important here to show is that within the same software environment, we are now dealing with two different type of networks. I said, this is the gas system, and this one is an electric transmission system where you may have the need of modeling different type of objects. For example, this is a very simplified case. We have only transmission lines, 20 demand offtake points, one generator, one fuel generator, which is a difference. In terms of portfolio of generators, there is a long list of possibilities that you have. If you're not interested in the type of fuel, you can use and pick the generic generator. What you just need to provide is how much power you want to generate. Otherwise, in this case, because I wanted to showcase the link between gas and electricity, I also introduced a fuel gas generator with certain properties. Let's go back to this. For example, you can select which type of fuel you want. In this case, you're going just to use whatever is available in the gas infrastructure. You can define heat rate function, fuel custom function. You have also other properties that are more related to economic aspects, but these properties are not used in the electric simulation, are used in the production cost model simulation. So that's why also it's maybe important to stress, you are still inside the same environment and you're using essentially the same type of objects, but your type of problem is different, physical simulation or optimization. So this further helps. I integrated in this tiny example a windmill, so generation of electricity from wind. I did this just to showcase quickly the possibility of having an already integrated capability of retrieving data about wind and about solar irradiance from online databases, specifically for solar related things. We have two options. Either is this PVGIS project, which is an EU funded, supported by the Joint Research Center project, or you have this NSRDB, which is kind of equivalent, but from the United States NRL database, covering basically the two of them are covering all over the world. And in the same side for more wind related things, you have the wind toolkit, again from NREL. Essentially what you do here is defining the latitude and longitude of the facility that you want to model. And through this interface, after providing some credentials you need to register on their website, you can automatically download the data and also kind of post-processing them so that you don't waste time, you just go straight to the point of understanding or simulating their behavior. Okay, let's check some other results. You may see now these blue links. These are the graphical representation of what we call coupling points, meaning I can run a gas simulation with its own scenario and get the results. I can run the electric simulation, get the results. But in this way, I would run each simulation as a separate exercise. Same provides you the capability of running combined and co-simulations. We will clarify this concept. A combined simulation means that an electric grid and a gas grid are considered together, And the two scenarios are merged and analyzed as only one problem. This provides a capability of modeling the interactions between the two systems. In this case, we have introduced a couple of elements, which are, we want to model the compressor station on the gas grid as if it was an electric-driven compressor station. So we need electric power to move it. The general technology is on gas, so it's burning gas to push gas out. We linked the underground storage operations to the electric grid. So whenever gas is injected in the storage or withdrawn from the storage, there is an electricity consumption. It is a demand on the electric grid. Without power, the storage cannot work. There is another, as I said, gas power plant, which needs fuel to work. So if gas is not provided in the right conditions, this gas generator cannot work and cannot produce electricity and cover the demand. And we have here also at the two other coupling points, we introduced electrolyzers that are transforming power into different type of gases. One is hydrogen and the other one is methane. So there are a lot of details about the efficiency of the electrolyzers and how they can then operate to inject the mixture in the gas infrastructure. And yeah, I know it's a little bit overwhelming, but I just want to show you maybe we go to the dynamic scenario. Once you have the grid ready, you can develop your scenario. A scenario is a set of constraints that you impose on the different objects. And what is important to note here is that constraints could be as straightforward as saying you need to produce this, 5. Or more time aware by saying you not only start by a certain figure, a certain number, but then you incorporate time using a time profile so that you can carry out a dynamic simulation. SAINTS allows you to carry out steady state analysis, and in steady states, the underlying assumption is that everything is in steady state, so it's perfect equilibrium, which is a good approximation for many planning and designing exercises. But if you need more, you move to dynamic simulations where time matters and the dynamic of your system can be better understood. There is a basic difference between the dynamics of slow systems like the thermal one or the gas one against high speed systems like the electric one, where milliseconds can make a difference. While in gas, you can just wait even 5 minutes or 15 minutes. Then the system starts to react. I'm not going into the details of all the aspects of this particular scenario, but I would like you to pay attention to these 2 lines, for example, where we showcase what could happen if you do want to have a higher logic embedded in your model. You could say, okay, my compressor station, in this case is a supply point. My supply point needs to provide me with gas at a pressure of 47.5. That's a legitimate condition. But what if I need to change that value because of some event happening during the simulation? Because of conditions that are happening in my network during the simulation and in a different point in my system. So we incorporated conditions that you can create and insert in your model, which will act as what if logic inside the simulation. It's running, but what if is happening this? Then I need to do something else, which is changing the control mode of my facility, and the system will act in a different way. In this particular case, we are saying change the pressure at the supply point based on the behavior of the pressure at the entry point of a compressor station that is 150 kilometers downstream. This is taking time and all the feedbacks in the system. I will just first run the simulation so that we can see you have a log window here with messages providing you feedback about what is going on. Well, in this case, everything is green. It means that there is a good solution. There's no violation. And we are now able to, okay, let me have a look, at least of some of the details of the network. So the different colors in the pipes are showcasing the level of pressure, while color of the nodes makes difference between green supply point and red is a demand point. The size of the node is linked to the magnitude of the amount of gas that is either injected or withdrawn. And maybe oh yeah, I forgot to put the arrows on. We do not forget that it's a dynamic simulation. So we can see within the time frame that we have modeled what is going on. The size of the arrows is linked also to the intensity of the flows. And you basically are looking at the direction of the flow in that particular time interval. Here I set as steps 1 hour. The simulation is being actually carried out on a 15 minutes interval of time. You can have the same type of analysis when looking at an electric, yes, we have it, an electric network. Here is all the setup with all the elements. I just want to show you the different profiles that are used for their simulations. For example, let's pick this fake point called London, and we are assuming within the interval of time of the simulation, this behavior of the demand level, which should technically describe the kind of increasing demand up to this peak moment, and then the demand goes down again. And you have the different components here. We can try to run the simulation. Yep. And obviously, we could have the possibility of analyzing again the direction of flows of the power in this case. Finally, and then I will close this, we would like to take advantage of the combined simulation. Sorry, it's going to be a little bit chaotic now because two networks, one on the top of the other. But the important thing is that you see, either you simulate just the gas in isolation or the electricity in isolation, or you combine the simulation. So you solve the two problems together and you keep in mind what is the driving element on each object. For example, for the gas compressor station, if there is no power, the compressor station cannot work. So if there is a kind of blackout on the power sector, the gas part goes to zero and the flow is stopped, well, goes in bypass the system. And this is modeled in one go. So I click and run the simulation. It's not very different from what is happening before, but now numerically speaking, I can combine the two simulations together and see this integration. For example, if we go here and we ask, and we ask to gas compressor C1 POVD, and we want it in kilowatt. We ask Saint to retrieve one detail, which is the power of the driver of the compressor station, and provide us the value in kilowatt as a power. And because this object is linked to the grid in this point where we have this demand, this is the demand on the electric grid that models the compressor station request. So because we carried out combined simulations, I should expect to have the demand on the electric grid equal to the power requested by the compressor station. Otherwise, there's something wrong. I hope not. Electric demand, CS1 P kilowatts. You see, they are the same because we solve one single problem. Let me redo the same exercise, this time by running only the gas. And we see now what kind of power is requested by the compressor station. Yes. Ah, yes. Okay. This should not happen. Yeah, it's blocked. Sorry. Ah. Yeah, it doesn't seem so, but this is an alpha version. So there's still some rough edges. By the way, the result would have been, we would have a POVD different from the previous one because only the gas system has different conditions. And because this is a gas-driven compressor station, it is controlled on the electric side, which is the one defining the amount of power that can be provided. Now, to solve this, I'm really sorry, but I need to kill it and relaunch it. Yep. Well, let's look at the bright side. We move directly to the other example. And I will try to be quicker.
Maybe I can ask a question.
Yes.
That has come from the audience online. They are asking if this works as well for district heating.
We will see the example. We will see the example of MV Park, where we can carry out a co-simulation which means we can run the heating system, use the result to feed in an electric system, run the electric system, feed the results back to the heating system, and back and forth.
Okay.
So that's the main difference between a combined simulation when you do just one run, because the two problems are mathematically joined together, in a co-simulation where you iterate between two different sets of equations. But yeah, it is possible. It's not going to get crazy again with me. For just a purely graphical description, in order also to show you an example of a system that is not as simple as the one before, in terms of topological and geometric complexity, I want to show you this example of Schuttenwald. I will load all of them. Okay. Let me first do this to show the network. The reason why I prefer to use the alpha is because we have further integrated some GIS capabilities, like this possibility of having coordinates and having a base map, so that it makes a lot of sense because it links directly to what Jorge showed you in the Hypergryd platform. In this example, we actually have three different systems. This one is the gas network of this municipality. You can see the numerical details here. We have 2,400 branches, so pieces of pipelines making up the entire distribution system of this municipality. And one supply point that is covering 1,500 nodes, which are different demands at the household level. Next to it, there is the electric network. This is a little bit less precise, meaning that the actual gas system is based on the data of the municipality. This is being inferred. All this data set is publicly available because it's linked to a paper that is being published 5 years ago. If you want details, just drop me an email or drop an email tomorrow and we will close the circle. On top of these two systems that are actually the core of the paper which is not by us, by the way, we add a tiny section of a thermal system over here. So now you would be technically able to, if I open a gas steady state scenario, an electric steady state scenario, and a thermal steady state scenario, you will be able to run gas steady state simulation, an electric AC PF steady state simulation, and a thermal steady state simulation. Maybe we can show this. Can focus. I'm not going into the details of the underlying simulation because this is not useful. What you see is basically that we are assuming there are 2 points where your system is supplied with heat, And you have many other points where the heat is used. There are some dead branches, which are very useful here just to showcase. Otherwise, everything will be the same color, basically. And we can have an idea, for example, of the thermal losses. So you can, based on your steady state simulation, you can have an idea of the performance of your system in terms of losses by looking at the different pipelines. In this case, when you model the thermal system, you do not only provide details about the system per se, but also about the environment through, for example, the ambient temperature. Here we are assuming that the ambient temperature is all over the area the same, and that the pipes are clearly buried underground. Maybe in the case of NB Park, you will see we can just play with this by saying that the ambient pressure for certain pipes, maybe the one along the streets, it's a certain level, and the one that are going into the buildings could be a different. Question?
A question is asking, the network topology is always an input of the model, or it can be the result of an optimization?
You should be here, not online. This is the kind of tough questions that I would like to have a face to attach to. It's a good question. Thank you very much. And the answer is not straightforward. In the case you see now, we developed the network. So the topology and the geometry is an input. But you could use the capacity expansion module, where you start with an initial idea of how you would design your system, and then you create expansions, you add elements. And that would provide you with an economic assessment of which option that you have put in, it's economically better based on your specific economic constraints. So this is not, to answer again, 90% of the time, the topology and the geometry needs to be an input from the user. But Saint allows also the possibility of, by combining production cost modeling and capacity expansion modeling, to have options to optimize your network. Then once it's decided which optimized version you want, you can take that and you can use it directly in Saint to do physical modeling. So you don't have to export from a software platform to another one. It's everything within the same environment. Yeah, I'm not very prepared on the thermal one, I have to say, but we have examples of electricity cases where we are combining these options of capacity expansion, production cost modeling, and then a unbalanced ACPF to see if the final system is actually working well. Let's close this as well and go back to another example, which is the MV Park. Okay. Now I don't understand why it's not opening. Sorry. We need to open the thermal is here, the electric one. Okay. So in this case, what we see is an example of the thermal network in NV Park and an example of the electric system also in ENVI Park, which is a little bit more complex than the previous examples because we have now not only lines, but also transformers. That's because within the ENVI Park, you have a kind of two-layered system. In this case, just to showcase some functionalities, there are some of the facilities that are working in a way that is not always the same as the reality. Like the PV here is working really a lot, and the hydropower facility that we have here. We may start by loading a thermal scenario. So we go back to the thermal. We look at the events. You can model essentially the flow, the heat power extracted, and the downstream temperature at each supply point, demand point. And you can play with a portfolio of supply points, meaning you can have this, what we call participation factor. So if you have two supply points in your system, you may say, okay, one of these needs to be used up to 90%, and the other 10% is the second supply point. You can switch, you can mix, you can have multiple supply situations with different participation factors. In the case of ENVI Park, we have only one supply point, and that's why we have a participation factor of 1. I said for each building here, the power needed for heating reasons. And we can run the simulation right away. And we set also the downstream temperature. So simulation, thermal. I just want to have this here. And let me go again and showcase the not friction loss, but the losses here. This gives an idea of, for this steady state snapshot, of what is the different losses along the pipes. We can have also flow velocity, if you are interested in that, or where is the flow rate in the pipes. You can change the legend type if you prefer this. If you want to go back to a bar, well, you can remove everything if you want. On the electricity side, we load a steady state scenario, and we run the simulation. And again, we have a simplified system where we can assess on a physical base consumptions, losses, and different strategies now in using the different options linked to getting power from the main grid, getting power from the hydropower generator that is here, or from the PV, which is linked to this particular node. If I select this, you see that at this node, we have actually two demand associated, plus the PVs that are injecting into the system. Let me just open one thing here and copy this. So we can check. Okay. Sorry, because it's not the case. But in this situation, what you can use is the possibility of linking the thermal results to the electric results. For example, you could say here, this is the entry point of the thermal system, which needs a pump to work. So the electric demand of the pump, we can associate it to this node, adding a new electricity demand. So once we have solved the thermal problem, either in steady state or dynamic, we could use the needed energy, electricity, for pumping that amount of fluid in the system as a demand of the electric one, and check if the electricity system is actually working within the foreseen range. Or if we could use to cover the electricity demand of that particular pump, maybe power produced at the hydropower, or if it's a sunny day that is coming from the PVs, or we need to pay something extra because we are taking it from the main grid. Or you could solve problems related to, I want to shift half of the heating load in one node from the existing technology of district heating to a heat pump, which goes on electricity. So how much electricity demand this is putting on top of the existing behavior of my system, and is my system able to withstand such new extra demand, or I need to lay a new cable to change a transformer to do some maintenance. I guess I went out of time pretty a lot.
No.
So if there are any question, yeah, please.
Thank you for your presentation. It's very interesting, and I'm curious what each algorithm you use to solve it. Because as far as I know, even the capacity that problem, just like thermodynamic problem itself is already
Everything is linearized. Everything is linearized.
So that the potential cost and time are increased. So if I remain all the
Yes. Yes. I think you know more than me because I'm not a mathematician, but yes, from the user perspective, that would have been quite straightforward to see by just running the shoot-and-valve example, because in the mock example, first one, the computation were pretty straightforward and simple because the number of nodes is around 20, it's small. When you already go 2 times higher, 2000, yeah, it's gonna take 30 seconds, 35 seconds. So that depends also strongly by the computing capacity of your system. We, as a software company, we have not yet made the big leap ahead of parallelizing everything. So essentially, the software is still using one core as a main element, and certain activities are distributed. But for the computation part, at least for the physical simulation, it's one core driven. For the optimization, because we are using Gurobi, that's a different problem, because in that moment, you just see, if you monitor the resources of your computer, that all the threads are used. Gurobi is very efficient from that point of view. But you are 100% right. The more you increase the topological complexity of your problem, the more the mathematical problem is big. Clearly, we have implemented the techniques to deal with sparse matrices. That's normal. But there is a limit to what you can do, for sure. The other question?
Yeah, may you just repeat the question, because
Yeah, sorry. The question was if it's correct that the computational load is linked and tends to increase with the complexity of the topological structure of the network. And the answer is yes.
Thank you very much. And from the audience online, we have two technical questions, and then we go on to a very fundamental one. The first one is, could we make scenarios of leakage and access of services, and could you show water pressure loss?
I will answer the part of the pressure. Yes, it is there somewhere. But please, if you can drop an email, because I'm not the super technical guy from the thermal one, so I will provide you with a better description of pressure losses. But the pressure is considered in the modeling approach. There's also elevation, which I didn't show, which is linked to pressure. The first question was,
could you make scenario of leakage and absence of service?
On the leakage side, no, we are not yet equipped with that. With the absence of service, I'm very happy to say yes. I'm happy because my background is in risk assessment of gas system, where we were playing in destroying gas infrastructure. So in that case, the absence of service was because we were blowing up facilities or pipelines. Yeah, you can do the same thing for the thermal one. For example, you could set either a node not in service by simulating the fact that there is something there so that you cannot provide heat to the final customer, or it doesn't make sense in the case of MPPAR because it's a very linear system. But if you have a mesh system, you could set not in service, one pipe, simulating repairing work or a disruption, and see if the remaining system is able to provide heat to the customers, or if there is curtailment, for example, due to the fact that you cannot meet demand with the supplied heat.
Okay. I don't know whether there are questions from the audience here.
Should I come over?
No, just shout.
Okay.
We can.
There's one thing I was interested in. Did you ever use it on a power plant or let's say a paper mill or something? So it's like a industrial site only. It's not like a large group of customers, but just like somebody owning a power plant has a paper mill or power plant, maybe actually connecting them.
Yeah. So the question is if we have had experiences of small scale applications to local realities, which are not distribution systems, like for instance, an industrial site of whatever type. And the answer is no. We do not have experience in that, in the sense that we never carried out a specific case study of that type. We don't even have clients incurring in that specific type of problems. We had experience of distribution systems, which are of the size of maybe 2-3 municipalities, and had the issue of revising their 10 years planning in order to face the problem of integrating more renewables or diversifying sources, and how to deal with that in their own reality. But yeah, it would be a very interesting case to see how the software behaves, how the level of modeling that we have up to now put into the description of objects could be able to answer that kind of specific questions. Because yeah, we have always to remember that modeling softwares are as good as the mathematical treatment of objects that you describe. So maybe we can answer a lot of questions, but not all questions that could be of interest of a specific users, just because our way of describing certain things is not as detailed as needed. A tiny example, and then I will stop. In the gas context, compressor stations are modeling things at a high level. We do not go into details of how many units you have in the compressor, if they are in series or in parallel, what type of driver type you're using. And the reason is that for planning purposes and designing the overall infrastructure, that's the type of detail that you do not need. You need a more kind of black box approach, so higher level. If you want to do more a compressor management analysis, Saint is not your product, it's not your tool. You go to other things like Simone or Synergy, which have 45 years of history in the sector, and they started as management tools. But just to stress again, for the sake of the objective of Hypergryd, I'm confident that the level of description that we have for electric elements, thermal elements, gas elements, it's really advanced. Especially if I randomly pick people in the street and I put it in front of Hypergryd platform, I hope he or she will be able to use it and to basically grasp what it's doing, even if he has no, say, engineering background.
Then there is another question, but we're running out of time. He's asking to share a base scenario, but this is perhaps not quite.
Well, yeah, we are, if you are so kind to drop an email, what I will do is to send you a screenshot. So we'll make a tiny movie showing better a dynamic simulation of thermal and electric together with some charts.
Perhaps you can drop your email.
Yes, I've already done it. Okay. Okay.
Thank you so much, also for your passion in listening.
Thank you. Thank you. Thank you, Nicola. And I think that now we can just wrap up for 5 minutes. And,
I'm going to and you can sit here. Sì,
Okay.
possiamo vedere.
So,
Sì, 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 facile. It should be on the desk. Mine?
no, I put it here. Wrap up. I don't see it now. Okay, doesn't matter. Not so important. Okay, my role is now to wrap up very briefly. I'll try to be shorter than the planned 15 minutes. For those who don't know me, I'm Marc Calderoni from Art Solution, also a partner in this project. First of all, I would like to explain a little bit from the, let's say, commercial perspective and usability perspective of the many tools developed within Hypergryd where we are. Because in principle, Hypergryd is developing, first of all, has developed a platform, which is basically what Jorge has shown at the beginning of this meeting, of this workshop. On this platform, you can model networks, 3D, and make a full digital twin of a network. Okay, that's the first thing. Entering, inputting all the parameters related to pipes, to buildings, roads, etc. Then we have a series of tools which are, to some extent, design tools. So tools you use at the design stage to optimize the network through energy simulations, mainly in different ways. We have 1/2 tools which are related to simulating energy communities within that specific network, including the interaction between the electric grid and the heat pumps, which are the main sector coupling component. And this, I think, answers to some extent the question about why a simulation model should be able to couple these two systems, the thermal and the electric one. I know we have here someone from RSE, so Italian Research Institute on Energy Systems. I think you can testify how relevant it becomes now to have co-simulations, because the more we go in the direction of renewables, of electric renewables, the more we have congestion in the grid, the more sector coupling becomes relevant, and heat pumps can actually consume electric power and turn it into heat. And this can be played with to some extent, because you can store heat much easier than you can store electricity. So that's, I think, the main answer to the question from the online audience. I was saying we have tools for the design of the networks. We have tools for simulating energy communities. And finally, we have a set of methods which will become, or partially are, a tool for to be used at the monitoring stage of, so at the in the operational phase. Now, as I mentioned at the beginning, these are not all available already on the market. Today, we have seen 2 of the 3 tools, I think, which are basically available now. So we have seen the platform, and we have seen encoord's Saint tool. The idea today was not to promote a product, but to show what the project did. But we, on purpose, deliberately decided to pick up these 2 commercially ready softwares, because tomorrow you may, if you wanted, ask for an offer for Saint, for example. I think the presentation of Nicola was very clear. The Saint tool exists since some time for gas and power networks. It's a fully commercial tool. Now within the project, so let's say co-financed with EU funded, with EU money, they have developed also the thermal grid assets, and in doing that, they have empowered their tool. So the last thing I wanted to say before we go to the questions, because there are, I think we launched 2 of the 3 questions, right? Okay. Both tools are developed by companies. IDP is a private company, encoord is a private company. So these tools are not open access, are not for free. You have now Nicola's email address. As for IDP, I don't know if Jorge, you would like to drop your email address, and they can ask questions sending you an email if they are interested in. So don't, you must be aware that these are also commercial softwares. And this leads me to the analysis of the responses to our two questions. Because the main purpose, especially of question one, was to understand what are operators in the framework of district heating and cooling currently using in terms of software. And the answers are quite interesting. I tried to group them, the answers, into three categories. I think we have, first of all, part of the answers basically tell us some of you are using tools like Panda Power, which I didn't know. I checked it on the web, but they mentioned Python, Energy Pro. So it's very powerful simulation tools, which are extremely open. You can simulate basically any energy system with them. So what, of course, you always have advantages and disadvantages. The advantage is you can simulate whatever you want. The disadvantage is there is a huge need for resources in setting up everything because you're basically programming. Okay, this is one of the three families of answers. Then we have some very targeted products, typically internal developments. And those are, I think, because I don't know them, I just saw the answers, those are probably very well targeted to do exactly what you need, but they are not flexible because as soon as you need to do something which differs a bit, and we are in a changing environment, changing framework because of the regulation, etc., this probably becomes more and more often compared to the past that we have to add something new. This is not something you can do trivially. You have to reopen the software, add things, and so you always have some development needs. And the third family is mainly AutoCAD. Of course, AutoCAD is a tool utilities probably use, but AutoCAD is solving part of the problem. You can do the modeling, but what about simulations? What about data processing, etc.? So these are the three parts of the answers. Now, these two tools we have seen today are trying to offer something in between, an intermediate solution. So they are more powerful than an internal software. They are not as flexible as Transys or Energy Pro or probably Panda Power, which unfortunately I didn't know, but are very targeted on district heating and cooling. And this is, I think, one of the big, let's say, results of this project. The second question was about what is mostly valued in using softwares. And I think unless things change, the most voted answer was the graphical user interface, which is interesting because it's still like this, right?
Yeah.
Okay. Yeah. So that calls for some effort in making the user interface as appealing and easy to use as possible. I think encoord's one seems to be quite effective in this sense, but of course one can always improve. Then comes the rigorous and detailed mathematical model. So first of all, simplicity of use. Okay, this was not a statistically relevant amount of people answering, but still quite interesting as a takeaway. And at third place, we have excellent documentation. So you didn't really show the document. Do you have some documentation in like in PDF, or is it?
Unfortunately, I need support responsible person. So yeah, we have documentation is structuring the reference guide that describes all functionality.
You want to come here to answer so they can listen?
There is the reference guide describing all the main functionality. There is a how-to section answer the question, how can I do this? Just in 3 steps, the answer. There is a tutorial section where you are guided through a set of functionalities that are tied together to a specific problem. And there is final one is under development these days, which is learn more. So the section where we explain which are the mathematical models. We provide the details of all the mathematical models of all the objects that are in the software. So we cover everything from the user that needs to be running the simulation right away in 10 minutes up to the one that has more academic needs to understand why this is happening. So the equation of the model is this. Thank you. PDF and HTML.
Okay, that's pretty much it. Just one clarification, maybe it was not clear during the workshop. The Saint tool can be, of course, accessed standalone, so you can buy the license or okay, according to the business model from Saint. Soon it will be also, as shown by Jorge at the beginning, accessible through the platform, as will be the other tools, which I'm not going in the detail of today, but we will have other future workshops, and we will also show, for example, the tool by Get. Was there a question? No. Okay. No. I think that's it. Anything you want to say before we close?
No, I think that we say goodbye to our audience online, and thank you very, very much for being with us in this couple of hours. And for the people in the room, now we are having a short comfort break, take some coffee and some water, and then we will have a tour of the NV Park facilities. So thank you very much all. Bye-bye.